that will be presented here. You're going to see a way of making them available, maybe using Google Drive. You're going to see that, and then we'll inform you later and give you the link for that. We have also the pleasure here to have Professor Raul from International Relation of the University of São Paulo. He's going to give us awards on how the University of São Paulo interacts in all these international area awards here. Okay, I give him the award, Professor Raul.
Good morning, and thank you, Professor Simões, Professor Achilles. It is a great pleasure to be present in this opening of the São Paulo School of Advanced Science of Renewable Energy. Of course, this demand of knowledge in this topic is something critical in terms of world, in terms of city, in terms of state. The University of São Paulo is a very huge university, like Professor Bajan probably mentioned. We are 92,000, around 92,000 students, and we have 1,480 agreements with 78 countries. All this international effort is in one single direction. We want to have at home, at the University of São Paulo, international environment. The presence of these students, professors, postgraduates, undergraduates, is part of consolidate international environment at the University of São Paulo, without borders, without flags. The only thing we want to share is quality, diversity of your knowledge, of your background. And on behalf of our international office, we call here international agency, we welcome and we wish you a very productive time at University of São Paulo. Thank you.
Good morning for everyone. My name is José Achilles. The first class, Professor Stephen Crowther, I call for him. The idea is we have all the day class about photovoltaic energy. And tomorrow we will go to Institute of Energy and Environment. It's near of that building. We come here, and after we will go to the institute to visit the laboratories, the photovoltaic station. We have a photovoltaic station of 500 kilowatts in this campus, in 3 types of installations. We will go to visit tomorrow morning. Okay, I will talk some words about the curriculum of Professor Stephen Crowther. Professor Stephen Crowther is from Germany, but he has a Brazilian heart. He works in Brazil, in Federal University in Rio de Janeiro and in other universities, and he has a company that works with photovoltaic equipment. They have installation in Brazil, and I will pass the word to Stephen Crowther, Dr. Stephen Crowther. A little curriculum. He's a professor of University of Paderborn in Germany, and actually since 2010 he works at Federal University of Rio de Janeiro in 1994 to 1997, and other universities in Brazil. He do his PhD at University of Berlin and the Master in Science in University of Munich. He has a great experience in photovoltaic projects and installations, and he will appreciate the class. Okay, I will pass the word to Professor Stefan Kroton to start the class. Thank you very much.
For the introduction, I just had my curriculum here, so I just stay over here. So this is about what I'm doing. This is our chair here at the University of Paderborn. It's called Sustainable Generation and Use of Energy. It's both related. It comes later in the talk. You will hear also about more use of energy, because it has to be coordinated with the generation. Otherwise, it gets very expensive. We work there also on energy efficient buildings, wind power, especially wind power monitoring, decentralized energy systems. It's a big issue now in Germany, because we have very inflexible, large-scale energy structure, which is not sometimes not able to cope with the fast fluctuations of wind and solar power. Virtual energy storage, so it has to avoid expensive storage and make it virtual. Load shifting via remote control of loads, yield prediction, and optimization of PV. So that's what we are doing. If you're interested, I have also some brochures with me. You can take one, or just take a look at the homepage, which is here. You can see here, this is our page here. Mr. Achilles, Professor Achilles also told here about my curriculum a little bit. So I've been here in Brazil almost 10 years. First 8 years in Cope or Mayotte in Rio de Janeiro, and then 2 years in Fortaleza. Fortunately not in São Paulo. I've been there for some events also. I know Professor Silas very well. So he visited his first step in 1994, when he just came back from Madrid. So what we are hearing today is very large. So we have got 3 lectures, each of them with 100 minutes. So I prepared 400 slides, so be prepared. So some of them I will jump quickly over it, because I saw, for example, for energy storage and fuel cells, we don't have to explain, you already get a special lecture on that. But it plays a larger role. Not only generation is important, but also the what we do with energy, how we get to the customers. Sometimes we have to store it, which is not very favorable, because it's now more expensive than the generation, as you will see later. But first we start on the potentials of solar energy, irradiance and so on. Then we go historically to solar thermal systems, concentration of solar irradiance. Then I come to photovoltaic energy conversion and the manufacturing of cells, modules, characteristics and performance. Then we come to the system side, how we interconnect solar modules to each other, what we need to connect them to the grids, explain a bit about inverters, and then mounting BOS on off-grid systems. This plays a really large role in the last years, because the solar cells always got cheaper and cheaper and cheaper, and the so-called balance of systems costs. They also decreased in price, but not so much. So, but these are now the most expensive part in the value chain. I will show you later on that. Come to this, talking about money, talk about market development. What are the markets? What are the prices and the costs? And then how we can optimize that, talking about performance, how we can optimize the performance, getting more energy out of it, and give some examples of optical, thermal, electrical optimization. Also, if we think about the other way, we can extend the lifetime of modules. So we talk about durability of PV modules and systems, what we can do in this direction. And while, for example, if we need light, we cannot have solar light in the nighttime, so we have to store the energy. So I give a little bit insights about energy storage and some recommendations about setup and common mistakes of setting up large-scale PV power plants. And the very end, I talk about research, new technology, and actual trends in that direction. Let's start. So first a question. What do you guess is the actual contribution of solar energy to our living presently? So if the world economy or the world population and some use solar energy, some not, and what's the actual contribution? What do you guess? For example, is it 1% or 5%? Who's for 5%? Yes, 1. 20%? No, if you take the actual planet system, it's actually 94%. This sounds really a lot. Many people are not aware of that. That's because without the sun, if we would switch off the sun, we wouldn't have solar energy, the whole planet would be freezing cold. In order to reach the presently global medium temperatures about 13 degrees, in order to reach that, we have solar energy. If we would do it by fossil fuels, for example, we would need a lot of energy. The moment we just have to, Brazil is not necessary, sometimes in São Paulo for heating, to come from 30 degrees to a little bit above. In Germany, the highest energy consumption is actually heating. We don't need a lot for cooling and for electrical. It's also not so much. The biggest sector is really heating. I said 30 degrees, yeah, due to climate change, already 14.5 degrees, so we just increased already 1 degree since I talked first about that. If we wouldn't have the sun, we would need about 15 times the world's energy consumption we have today, which is already a lot, which is 429.4 exajoules. Remember exajoule? How much is it? 10 to a power of? 18, exactly, 18. 10 to the power of 18, a lot of joule, and we will need 15 times of that. So it's really a lot, and we just have to do it one time to substitute the existing rest energy consumption by solar energy. I talked about fossil energies. If you think about fossil energies like coal, and gas, and oil, where does it come from? Actually, it's a long-term converted solar energy, because it took the planet about 150 million years to convert all by photosynthesis to create all this biomass and the animals and so on, which later have been turned within billions of years into fossil fuels. And we burn at a very fast rate, so we burned more than half within 200 years, and it takes 150 million years to recreate. So that's another good sustainable way of energy use. Best would be if we don't wait 150 million years, if we use the solar energy directly. Give you some examples. I know just why you use solar energy. There's also, I think you're well aware of that, greenhouse effect, that due to the fast emission of carbon dioxide in the atmosphere, we have this greenhouse effect. Here the infrared radiation can escape through the atmosphere and heats up. This is a prediction how much the temperature will increase. Presently, we have already 1 degree, and all agree that if we have more than 2 degrees, will be quite serious damage on the planet. So here we see the 2 degrees limit. What we already observe, here for example in the United States, that the crop yields fall due to short of water. Also very obvious is that all the glaciers are melting, no matter whether it's on the Alps or whether North or South Pole, you see directly. And also we observe here in Northern Africa and sometimes also down in Brazil, we have water shortages. So this is also related to the long-term climate change. And at the end, if all the ice is melted, we will have rising seas, which will happen not now, but later, if it's melting. And then also there can be abrupt climate change, because you know, if you have a drink, if you have a caipirinha with ice, and if the ice is melted, the temperature rises very fast, because the ice serves as a kind of cold storage. So as long as ice is present, when the temperature is kept very cold, it's like phase change material, but as soon as a lot of the ice is melted, then the temperature will rise at a much quicker rate. Species of extent we observed in a longer time also, you see storms, droughts, fires and heat waves. And as I told you already, just it could be abrupt climate change. People mean whether they're 2 degrees or maybe at 4 degrees when we have the rising sea levels and so on. But it's in general, it's a thing we should avoid. As I told you already, we could convert solar energy directly into the energy we need. That's actually this 429 exajoule we need for the planet. And this in comparison are all the fuels we have. So we have oil. If we put this perhaps 40 years or 30 years, there's a lot of discussion about this, whether we use how much does it last, but you see it's limited. Also natural gas is even more limited. Coal lasts a bit longer, so people think about maybe 200 years if this doesn't increase. So now we have increasing energy consumption worldwide. Some people think also nuclear power would be a solution, but we have many problems with that. There's nuclear waste, proliferation, and also the resources are not so big, so it's not a solution for always. So, what we can do against it, just take a look at the sun. That's the solar energy which comes in with 1 year only. So this is only not like these resources, which took 150 million years to create. This is 1 year only. So much more than all resources we have for all time. And about 15,000 times the energy we need if you convert it by 100%. Even if you convert it by 10% only, it's more than 1,500 times the energy we need. So if we would use a very conservative estimate, a very bad efficiency, 10% conversion efficiency of photovoltaics, so laboratory cells now make 30%, you can buy easily in a store 20%, but it's calculated with 10% of conversion efficiency, also including space in between the solar modules and so on. This is Africa, this is desert here, nobody lives there, this is desert of Sahara. And just to supply the whole world with energy, not only electrical energy, but whole energy for transport, for heating and so on, we would need that square. That's quite big, 300 by 300 kilometers, so not small, but it's feasible. It's not really something completely out of range. For Europe it would be that. For Brazil, interestingly, Brazil has about the same energy consumption as Germany. Germany only has half of the population. We consume a bit more because, as I told you, we have winter and so on. And, but you need just this spot covered by solar cells. It's not really a good solution to do it like that, because you have to store the energy, because you have only during daytime, nighttime. So there was some ideas if you distribute it around the planet. This is that one. So this is some power plants which are distributed here. One in the Sahara, one in Saudi Arabia, one in Australia, one here in Mongolia, one in North America and South America. And if you interconnect all those, you have a power supply which goes on for 24 hours. And also because it's north and south related, you have also running it through the whole year. So there's no, you avoid seasonal changes by that. So that's not cheap. It's about 20,000 billion euros. So it sounds a lot if you compare it. But if you, for example, take into consideration the so-called war for oil and so on, if you go to Iraq and Afghanistan and so on, which was basically, even the Americans admitted that this was a war for oil, it costed alone 1,400 billion euros. to pilot. So this is already not really 10%, but almost a share of those. We would have the whole world, so there wouldn't be any fight anymore for resources, because there would be enough power for everyone and forever. These are the cost developments of this. Quite interestingly, this is a graph from MIT 10 years ago. So this was about the cost estimation. So they were in 2005. They estimated it will be at 20 cents US cents per kilowatt hour. It's about similar to euro cent. As about the euro is about 14% more than the US dollar. And so nowadays we would have in the vicinity below 20 cents. So this was basically true for all the other resources we have, but for photovoltaics, due to a large development in the last decade, this changed a lot. So now we achieved in Germany 6 cents per kilowatt hour, so it's much less than this, and in sunny locations, the last tender, I come to this when I will talk about the market development, was even at 2 cents per kilowatt hour. So that's even cheaper than thermal energy. So if you just burn something, it costs you 2 cents just for the operation of the power plant without generation of electricity. That's quite interesting development, but I come to this a bit later. First we talk about our resource. It's both valid for solar thermal and photovoltaic applications. So we have our sun, which is this is a fusion reactor which works, reliable, since 4 billion years. It will work on for 4 billion years. And to a safe distance, about 150 million kilometers away. So that's not really adequate, this high. So in truth, the Earth would be much smaller and the distance would be much higher. So it's a bit distorted. Even the light alone from the sun to the Earth takes about 8 minutes to arrive there. So it's just a vast distance. If you go with the speed of light, it takes 8 minutes to come there. Even if you consider that they are arriving 178 petawatt, so 10 by power 15 watts on the planet Earth, 15,000 times the world's energy consumption. And the Earth is wasted, there's just space here, and it's quite astonishing how big the power is here of the actual fusion takes place in the middle of the sun. It takes place at a very high temperature, about 15 million degrees Celsius, or 15 million degrees Kelvin. What we see actually is just the very relatively cold surface of the sun, which is at 5,800 Kelvin. This creates that spectrum. Mr. Planck invented this formula about 100 years ago. It depends on temperature. When you go, for example, if the sun would be irradiated with the middle of it, it would be very harsh X-ray radiation, and I think a human habitat would be possible on the planet. While we have a quite cold surface and receive the irradiations at a very moderate wavelength, so this is a visible part starting from 400 nanometers. Before that, that's we call ultraviolet, and then it goes up to 800 nanometers. Above, beyond that, it's called infrared. This visible part, so a big share of that, the human habitat developed it because it wants to profit most of the highest solar radiances available. We can't see the ultraviolet, we can't see the infrared, but solar cells can. So therefore we talk not about sunlight, we talk about solar irradiance or solar radiation when we talk about photovoltaics. When people mix it up, they say how much sunlight you need. Yes, the solar cells can work with sunlight, but for example silicon can work up to 1,150 nanometers. So it can work with infrared radiation too. And therefore we don't call it light. We're talking now in this session about solar irradiance. So this is the effect of the temperature. As I mentioned already, about 6,000 Kelvin creates that spectrum with a maximum of 500 nanometers or 550 nanometers. If you have old-fashioned light bulbs, it would be good if you would have a material which could withstand that, then you would have the same spectrum. But there is no material which can withstand that. So the old-fashioned light bulbs, they have the best materials is what do you call it? Bismuth and sometimes this is Wolfram. I don't know the English word Wolfram. There's some materials and metals which can withstand about 3,000 degrees, but the maximum you can get, otherwise it gets liquefied. And therefore, each light bulb has a spectrum like this. So remember, you have here from 400 to 800 nanometer, that's a visible part. So the efficiency of a light bulb is very low, because the largest part by light bulb is infrared emission. So it's creating much more infrared radiation, so it's more of a radiator, infrared radiator heater, rather than a light source. Nowadays it's much better because we have LEDs, so they have almost a factor of 10 better in efficiency, and they can really create the light in the wavelengths the way you like it. Just to give you an idea how this works, this was just explanation of this plant formula. Then we have another, so this was about the spectrum. We talked also about the distance and the irradiance. Additionally, we have another effect. The sun, the Earth is turning around the sun, but the axis, the auto-rotation of the Earth and the rotation around the sun are not in parallel. There was a big event, possibly this event some almost billion years ago. The moon was created. There was a crash with a almost Earth-sized planet with that, and the moon was created, and it also tilted that axis from parallel to 23.5 degrees. So we have not an equal rotation. Some planets on the they have that, but the Earth not. So we have here a tilted rotation, and we have the moon here, not shown here, and so we have some special conditions. So we have here in December, we have that the southern hemisphere, the large part of Brazil, is looking more towards the sun. So we have summer there. If we go here to Europe, Germany, North America, it's looking away from the sun. So here it doesn't receive that much sun, and therefore we have winter there. Vice versa, it's nowadays here, 21st of June, so we have the northern hemisphere looking more towards the sun, and the southern hemisphere is looking away, and so theoretically we have winter. Not really cold here, but if we go more south to Buenos Aires or to Porto Alegre and so on, there's quite, it's getting quite cold these days there. Then we have two other dates which are really important. This is the 21st of March. There the sun is exactly perpendicular over the equator. And at that date, all cities in the world, they receive 12 hours of sunlight and 12 hours of night. This is called equinox. The same occurs here at the 22nd. It's not totally symmetrical because it's 22nd of September. And then we have same, so the sun is shining perpendicular on the equator, and we have 12 hours daylight and 12 hours nighttime in all parts of the world. Here we have a value that's a so-called extraterrestrial irradiance. That's the irradiance which a satellite sees. So if you have a satellite, they receive 1,365 watt per square meter. So this is an exact value because there are no clouds and so on. Also, they're looking usually perpendicular to the sun, and so you can have that value. So that's the maximum we can theoretically achieve. If we wouldn't have an atmosphere and it would be right directed, so if someone says he has 1,400, it's not possible because this is the irradiance which arrives above atmosphere on the Earth. So these are some basic outlines here. If we are just now positioning ourselves on the Earth here, somewhere here, and look towards the sun, we make some agreements. So we say, okay, the sun has a position, some elevation. We call it elevation of the sun, gamma S. So S for sun, and gamma is the elevation angle. And also, it's looking in a certain direction. North would be 0, south would be 180 degrees. This is called the azimuth, solar azimuth. This is important, for example, if you have here the so-called, you want to check the influence of the atmosphere. So if the sun shines perpendicularly to the atmosphere, there's some filtering by the atmosphere, the shortest way to get through the atmosphere, so the filtering is lowest, and we call that air mass 1, AM1. So it goes through here. For any other position, we have a longer way through the atmosphere. For example, here, this is 1.5 times the way through the atmosphere, so the filtering is also stronger there, and it reduces the solar irradiance, so the quantity of the irradiance is reduced, but also it modifies the spectrum of the solar irradiance. Come to this next. You want to calculate it here, this AMX is just 1 divided by the sinoid of the elevation angle. So this is about equivalent to 42 degrees of elevation angle, AM 1.5. So you see a difference. So this is the extraterrestrial radiation called AM0 because it occurs here above the zenith. Here would be AM0. So that's the spectrum of that. So it's not perfect black body radiation, but almost. And then we have here AM 1.5 radiation. So first see it's less, but you see also that there's some almost complete absorption for some planets. This is different components of the atmosphere. Most famous is ozone, which absorbs the ultraviolet part, but also water vapor or even carbon dioxide. They are responsible for the reduction here. And they create a different spectrum. If you continue that, you can go, for example, if you go close to sunrise or sunset, or here, for example, for an elevation angle of 10 degrees, it would be, if you are at the equator, for equinox, it would be 40 minutes before sunset, then you would have this spectrum. Colored a little bit in the color where it appears, because this is our famous color we have on sunrise and sunset, it's red. So you have here we have almost no radiation in the ultraviolet region. Most of them occurs only after in the vicinity here on 800 nanometers, and this appears red. So human eye says, okay, we have nice sunrise and sunset, and this is due to this effect by this air mass, because it doesn't absorb equally. It absorbs the blue part a bit stronger than the red part. And here for the intermediate values we see this. Why I'm telling you this? This is also because the solar modules or solar cells are selective. They do not convert at the same rate all kind of irradiance. Depending on the cell technologies, for example, silicon has its maximum efficiency in the 800 nanometer region. Crystalline silicon is here, most effective. While other, for example, amorphous silicon is more sensible in the blue part or other technologies. Therefore, we have to talk a little bit about that, about telling that. Also, we have the so-called standard test conditions. That mean we have a fixed spectrum. This is called AM 1.5, which we use for comparing solar cells. Otherwise, it could be cheating very easily. You take the maximum efficiency of your cell, for example, you take a silicon solar cell, you put in a laser with 800 nanometers, and then you would have almost 100% of efficiency if you give an illumination without any UV content and so on. And then you would have just a very good quantum efficiency of that. And therefore, there was agreement that it's AM 1.5 where you test the solar module, terrestrial solar modules. Formerly, most of the photovoltaic development occurred in space 2 decades ago, and so there was AM0 was the standard spectrum. But now it's for terrestrial application, it's AM 1.5. But I come to this a bit later. This, for example, for Berlin. So you see the different positions of the sun. In São Paulo, it doesn't differ so much, but in Berlin, in winter, for example, the sun is only 14 degrees above horizon. So just this very red light during the winter time, and only for a very short period of time. This is the according air mass here. So in Berlin we never get AM1, just best we can get is nowadays, the 21st of June, AM 1.15 at an elevation angle of 60.8 degrees. And AM 1.5, so you don't have to buy an expensive solar simulator, you can wait for the date and then you can also put your solar panels there and test it almost with standard test conditions. This will be possible here in Berlin for midday, the 1st of April or 12th of September. There we have exactly 1.5. Also it's also possible for São Paulo. Fortunately, you don't have a slide for that. This is just the solar azimuth angle for different kinds of year. So here we are now in this direction, we are now in these states, so already sun goes up at 4 o'clock in the morning these days in Berlin. So you, and only goes down at 20, we even have daylight saving time, it goes down at 9 o'clock. So we have if you are going holidays in Europe, now is the best time to go, because you have a long sunshine period, so almost 15 hours of sunshine during the day. Don't go there in December because people have holidays in Brazil in winter and they're totally disappointed and say, it's even for Germans it's disgusting. It starts at 8 o'clock and already at 4 o'clock it's night already. And the sun only goes up, and this is even for clear sky. Most of them is not clear sky, it's even worse than that. So it's so this is quite a high fluctuation. The difference in Europe between summer and winter is quite big. If you go to other locations, for example, we go more south now, we go to the African continent here, Cairo. So here the variation is much less here. It's just lowest position is at 36 degrees. Highest position is not AM1, it's not 90 degrees, but close to that. And then it looks already different. So here sun goes up very quickly, and also it stays more around going up in east and going down in west. If you go back to Berlin, you see it almost goes up here nowadays in northeast and goes down in northwest. Almost makes a circle. If you go more north, even you can have a complete circle. You go above the polar circle, 70 degrees, you have a complete circle, and sun never sets in for a period of time. While in winter, it doesn't rise at all, so it's a disadvantage. So here it's for Rio de Janeiro. It's a bit different. It's about the same graph, but polar coordinates here you see here your west and east, and here you have the different dates. For example, here 21st of June. This is winter in most part of Brazil. So here you have the different dates. So here you have it goes down at 5 p.m. and goes up at 6 a.m. And that's the equivalent for Rio de Janeiro. And you see, because it's directly at 25 degrees, 25.5 degrees south of the equator, you have perpendicular irradiance at the 21st of December. You can calculate this. The slide I use for my students. I think you will publish the slides also later. So if you make an app or something like this, you can also make this kind of graph. These are the formulas for that. Just you have to use them. I don't go to the details of it. Here, even you can consider the refraction of the air, because the refraction of the air just some distortion, and this is also considered here. This is from the astronomical almanacs. You can very accurately calculate the position of the sun, or the apparent position of the sun you have, which is relevant for your solar energy conversion. We talked only about direct irradiance. You don't have only direct, because a lot of it is scattered or absorbed in the atmosphere. We have a large part, even in sunny areas, we have 30% of our participation of diffuse irradiance. In Germany, in winter, we often have 100% diffuse irradiance. You don't see this directly. And also, we have another component, which is called albedo. This is a reflective irradiance. So if you have a very reflecting ground, like snow or glacier or white sand, it can make us, depending on the position of that, of the receiver surface, what the inclination angle is, it can make also a significant impact on the global irradiance there. And for photovoltaics, if you don't have any concentrators and so on, this global irradiance is relevant, which consists of direct, diffuse, and albedo irradiance. All of them are relevant. Especially now, come to this later at the very end of the lecture, when we talk about bifacial solar cells. they can profit a lot from albedo. So it's quite good to know. This has been ignored for 2 decades, but now this albedo becomes more important because if you can receive also irradiance from the back, this can have increased the energy yield by 10 or 20%. So this is just a first estimate. So if you see a heavy cloud, it's about 50 to 200 meter per watt per square meter on the radiance level. If you have 200 to 700, we maybe have some clouds. If you have clear sky, it's mostly between 700 and 1000 watt per square meter. So without just looking in the sky, you can quickly guess. Actually, we do it more accurately. We have a pyranometer to measure that. I come to this a bit later. Also, I think tomorrow Mr. Sillis will show you pyranometers and measuring stations and so on. This is some plot here where you have the share of diffuse and direct irradiance in Cairo. So you see here, there is even in Cairo, which is usually the desert there, and then you have desert is close, it's actually a big city, but there is even a high share of diffuse irradiance. In Germany, sometimes you have only diffuse irradiance. So here's what I said. It's most important is the global irradiance, and this you see for different locations on the planet over the year. We start in January here, go to the Sahara Desert, it's winter there, and irradiance is at about 5 kilowatt hours per square meter per day. So it's daily irradiance. So if you have like half of this table here, put in the sun, and it receives 5 kilowatt hours. So if you would convert it by efficiency of 10% with your photovoltaics, you would have half a kilowatt hour coming out of it. And it goes up to 8 kilowatt hours per square meter per day. Here, if you go to London, or it's very equal to Germany, you would have this one. So winter is really bad there, so it's below 1, only half radiance, so about a factor of 5 less. Summer is not so bad, so the difference is not even a factor of 2. And this poses problem, for example, if you have locations like this, London, if you want to have a full provision of solar energy during the whole year, because you have to cope with that. Here, summer doesn't pose any problems, but the winter is a real problem. And if you want to make autonomous systems, which have to work without grid connection through the whole year, you have to think about enormous energy storage capacities. I'll give you an example later, how to calculate that, but this nowadays is the most expensive part, because storage is getting somehow cheaper, but solar cells got much cheaper at a much quicker rate. And I'll give you some examples later for some autonomous systems. This is for Brazil now, compared to Germany here, Hamburg. Here, let's see here now summer, so it's not so bad now in summer. So it's even better than Rio de Janeiro at the moment, the irradiance. But problem is also winter, similar to London, here below 1 kilowatt hour per square meter per year. And here, Rio de Janeiro is more than 6 times more of irradiance. So here the minimum is here nowadays at a rate of about 4 kilowatt hour per square meter. So if you calculate with 4 kilowatt hour per square meter, you can supply energy for the whole year and have a surplus in summer in Rio de Janeiro. Sorry, São Paulo is not here. We have some other, Porto Alegre is here. So São Paulo is somewhere between Rio and Porto Alegre. And Fortaleza, so this is just here for Porto Alegre, you have a quite low minimum, 3.2 kilowatt hours per square meter per year. Any question? No.
The name of Indian name.
Yeah, okay. If you have any questions, yes, please.
Are there any questions?
Yes, please. Germany or for solar Yeah, so example, this is used if you want to have the fast equalization over the year. While nowadays, in the decade, people are more looking on that one to have because most of the compensation tariffs are paid by kilowatt hour. So the people want to have the maximum yield during the whole year. And for this 30 degrees is optimum for the bill. Also, if you consider diffuse irradiance, if you consider direct, it's more better to do it more steeply. But if you consider diffuse irradiance, it's more tend towards horizontal. If you would have only diffuse irradiance, horizontal is the best position. This is always a compromise, whether you want to capture most of the direct irradiance, so you're right that it's better to have a more steeper angle, or you want to have optimization of lower irradiance, and that includes diffuse irradiance. And they are a little bit of a trend towards horizontal. But this computer program, if you are going to use PVSys, and you can all modify it, and it even automatically finds the best position for you, depending on the location. It's not only the latitude, it's also the diffusity of the air. So some area, if you go to cities, there's a lot of diffuse irradiation, so it's better to put more in a horizontal position. You can also do it mathematically. Not the direct, you can do mathematical. The diffuse is quite difficult to do it really mathematically. But these programs like PVSys or hydroelectric do it mathematically, or PV solar we see later. Any other questions? But for equalization, you're right. Sometimes I even suggested it comes in the very end of the lecture. If you want to have a equal grid load over the year, it's better to lose something here, but to have a better grid use during the year because you have more equalized production over the whole year. That's an issue in Germany, but this depends on economical thing because this is paid, and the other one, if you do have a constant grid load, is not paid yet. So this is not this is good for the grid of energy consumption, but the investors in solar power plants, they don't get any money from it. Not yet. So this is a discussion. They should be paid for first for flexibility, but also for, let's say, equality or something like that with power production. So you see here, this is the Brazilian grid load here. It's quite a bit old when I worked in Brazil about 10 years ago, so most of the energy is consumed during nighttime. Unfortunately, this is only irradiance, but we can call here just something part. This is only irradiance. Brazil here, so you can call this. Unfortunately, speed we cannot. We have to store the energy or whatever. We have to shift consumption is also right here. This is also the this is also for, I think this is what one of the graph I made comment, this is the irradiance, this is the azimuth deviation from course, if you just look directly north and you have an angular of inclination of 25 degrees, you get the maximum here. Rio de Janeiro, this is for photovoltaic conversion efficiency of 10.7%. Nowadays it's almost double, so our photovoltaic modules they have almost doubled it, but if you take this conversion efficiency, you get 192 kilowatt hours per square meter per year out of it. If you incline it more, like you suggested, for example, here, you get a little bit less. But the difference is not really big, so from 192 to 185, the difference is not so big. It gets really rough if you go to facades. So if you put it to a facade, and then the radiance is really low here. So then you have here, not only radiance, it's already power production, sorry, not mentioning radiance, it's already photovoltaic energy power production. So here you see that only half of it. In Rio, the more south you go, the less difference you will have. So if And this is the azimuth angle, since you already know. And this is the angle between the sun and the normal of your perpendicular on your receiving surface. But this is important, for example, to know exactly where you have some obstacles here. So if you have some trees in front of it, so you can calculate it. I jump quickly over it because the Brazil side is more higher, but this is a serious problem in Germany because the neutral side is very low, and you always have to consider these objects here, for example, another house, trees, and so on. So first you measure the inclination angle of those obstacles here. So this obstacle goes up to here to 25 degrees, position of that, and then you transform it into a graph here. Here's the graph you already know. Here, so in summer there's no problem with these obstacles, so here the side is much higher than these obstacles. But here in winter, you see that the winter period is almost totally shadowed by these obstacles. And there's a little radius anyway, but it's even most of the day is even shadowed by these obstacles, and you almost get no solar radius during that period in half of the year. Also, these computer programs do it now automatically, so you just have to give it, you have to register, or you can take a picture of it and calibrate it and scale it, and then these programs calculate automatically the effects of such obstacles. There's not only field obstacles, you can create your own obstacles. For example, if you have various rows of solar modules, you build a big power plant and you have module 1, module row here 1, module row 2, and so on, and then they can create their own shadows. Depending on the distance they have here, this is by T, so you can here, this is a nice thing for the students here, how to calculate how much for given elevation angle of the sun, what's the minimum want to do something with the irradiance. We first start with solar thermal. So this has been used since 2000 years. And take a look at it. So this is not 2000 years, this is 130 years gone. This was on the Paris World Exhibition, and this was all quite advanced system. So this was first a concentrating system, then you created vapor, and this vapor was powering a steam engine, and they used this steam engine to power a printing press. So it was quite a complex system already, and it worked quite well during that time. So talk about concentrator. So you have here a parabolic concentrator. You have two areas. So one is the effective area of your parabolic mirror, and then you have your focus area, or sometimes only a focus point. So theoretically an area of 0, and then you can do something with it. So also you don't have to make a solid reflector. You can also split it up in parts and have here some tangential reflectors here, and then you have, for example, a tower absorber here, and you can make a very large scale. Or you have here not only a focus point, but a line of focus. Such a concentrator also gets built up with like this, and here also focus line correctly. Stop again. Okay, so this is the concentration, the conversion efficiency. No, that was okay. So this is the conversion efficiency of the concentration ratio. Concentration ratio 1 means just you have a flat plate connector without any concentration. And then you have here 50, for example, and then if you have here the maximum achievable temperature is about 900 degrees here. For normal a flat plate connector, temperature cannot go up more than 180 degrees and so on. This is the regular limit you have there for the concentration. And this is logarithmic scale. So we have here the maximum you can achieve is a maximum surface temperature of the sun. You cannot get more than that to determine thermal reasons. So you cannot create a higher temperature just by concentrating the lights. By that, so this is the maximum you can achieve that by a concentration ratio of about 30,000 or 40,000. Some examples for that. This is here, for example, made in the 50s in France. So this was before France opted for nuclear power, basically to military reasons. They spent a lot of money in solar power. It's quite interesting. If you it's on the border between Spain and France, in the Pyrenees here. And they have a large building, about 40 meters high. This building still works here, and you have a very large mirror here. And then you have a whole hill here covered with mirrors here, 33 mirrors, which reflect the sunlight onto this big house, actually, a 7-story house, and then it gets reflected at the focus point. And the concentration ratio is 16,000. So you have on 1 tiny square meter, centimeter, you have 1.6 kilowatt. And the temperature you can achieve there, realistically, is 3,000 degrees Celsius. And this was really planned for energy production, like the vapor machine we saw in the first slide. Nowadays, it's still used for metallurgy, because here you can switch off and on very high temperatures, just by adjusting the mirrors a little bit. And also they have a possibility to shut off the incoming light, and this is quite welcome for metallurgy research. This is another example from the 80s, the last century. So this is in Death Valley here in Arizona desert. This was this time quite large power plant here, 354 megawatts, a mirror area of 2.6 square kilometers. This is just a focus line here. Usually this absorber is not white, it's black, but due to the high illumination it appears, because there's a reflection on the surface, it appears to be white. And then you have here a steam turbine at the end, and then you can create electricity and a rate of 10 cents per kilowatt hour. This was cheap during that time because photovoltaic at that time costed about 10 times more, €1 per kilowatt hour. Nowadays, photovoltaic really got cheaper than that. So this is the power flow, so nice for the student to calculate what's the reflection and the absorption and so on. The thermal losses we have here, convective heat transfer, radiation and so on. You can also concentrate via Fresnel lenses, for example. This is also possible. You don't have to have a parabolic mirror for doing that. Now we come to take a look at the energy fluxes. So we just discussed a lot about incoming irradiance, whether it's concentrated or not, about the reflection a little bit, and then if you have a transparent receiver, some of it some of the irradiance passes it, and then for solar thermal application, this is our main destiny here, that you want to convert it into heat energy or heat flow. We have photovoltaics, we want to have a large part being converted into electrical energy. So this is, for example, the energy flow inside a flat plate collector. Very simple ones, you can purchase here everywhere. You have here the 100% of incoming irradiance, then you have the cover glass. According to the refractive index of conventional glass, which is 1.54, and the air is 1.0, you have a reflection of about 4% here for the first interface. If you go to the second interface, again 4%, so you lose here about 8% of irradiance due to reflection. This depends also on the incoming angle. I come to this a bit later. Also, if you don't buy a very expensive quartz glass, here you have some absorption here up in the vicinity of 2%. And then you have the absorber, which is not perfect, so you lose some reflection also on the absorber. Then you have of this is now converted into heat, and this heat is also not perfectly transmitted. You have some natural convection because to the hot absorber, air is getting hot, and it gets a buoyancy because the density is lighter, it goes up here, and you lose about 13% of that. Also, you have some thermal radiation of the absorber plate. Usually there's much more, but while we have a cover glass here, this is a kind of artificial greenhouse effect here, then we have only 6% of losses. But then if it would be open, this would be much higher. Also, you have some thermal conduction depending on the quality of your system. Here, for example, typically are 3% of losses. In the end, you have about 60% of the 100% which comes in, which is not so bad if you compare it to photovoltaics. Formerly it was only 10%, now it's 20%. This depends very much on the temperature and the model. I come to this a bit. So you see here, for example, for a standard collector here, first you have the optical losses, which are in the vicinity of 8%, plus the reflection on the absorber. And here are the thermal losses. The optical losses are not temperature dependent, so it's independent from the absorber temperature. It's always the same amount of losses in the vicinity of 8% plus 4%, so 12% losses here. Not more, 14% of losses, optical losses here. And here you have the thermal losses, which depend on temperature. The higher the temperature is, the higher the losses are. Here, for example, at standard test conditions, which means we have an irradiance of 1000 watt per square meter, you see you can achieve a high temperature difference. But what happens in winter, when your heat is most needed? For example, here 200 watt per square meter, so you only achieve a temperature difference of 40 degrees only, and this only if you pump the water in a very, very slow rate through the collector. This means you have a very low efficiency here because you don't pump a lot of water. The highest efficiency if you have almost no temperature difference, so you pump at a very high rate. So the losses are low, but you cannot profit a lot because the temperature difference you created is very low, but the nominal efficiency is quite high. If you go to different technologies of these collectors, you see that differ significantly. First, let's talk about uncovered absorber. You just have a plastic tube, you put it into the sun. Nothing else. No cover, no glass cover, nothing. You see here, for very low temperature difference, the efficiency is even better than all the others. Can you imagine why? Yes, all light is absorbed. There is no reflection by the glass sheet because we have optical losses which do not occur here. Therefore, this is a good, very good efficiency, 95% or so. This is very good if you have, for example, if you need a very low temperature difference. For example, swimming pools in summer, you only need to increase temperature maybe by 5 degrees, or people are happy. So this is quite good for that. You don't have to buy an expensive vacuum tube collector or something like this. This is sufficient for that. So it really depends on the application, which collector you should use. If you need a high temperature difference, and especially also winter, for example, for heating purposes, then you should switch to a different technology. For example, here to a flat plate collector. So we have here first here this dark line is the flat plate collector with one covered glass only, non-selective. I've explained this selective and non-selective a bit later. Then we have with two glass, it's already significantly better, but you see already here the difference here, because you have two glasses, you have double the reflections. And so here, for small temperature difference, the efficiency is not really good. But if you have high temperature difference, for example, you want to create a temperature difference of 100 degrees, it's not possible with the one glass collector. You have to have a two glass collector, and here efficiency is not so good, but not so well. And the best is here, if you have a vacuum tube collector, then you can create a temperature difference of above 200 degrees. Why is it so good, vacuum? Which of the losses are you avoiding to use? Which of the losses are eliminated? Yes, here, natural convection is, you don't have any more. Thermal radiation you still have. It's a bit reduced if you have second cover glass and so on. Now come to the selective and non-selective. For this I go back to the spectral level. So we have here the wavelength of the irradiance in a logarithmic scale here. And here again we have the black body radiation of the sun here. So it looks quite symmetrical in the logarithmic scale here. And here we have a non-selective absorber, which is just black body, which absorbs all wavelengths at the same rate. And there is a law called that the emission of so for black body emission is equal to the absorption. Alpha is epsilon. So that means if you have a high absorption, you have a high emission also. That means we have the advantage here, that area, this is very welcome. We absorb all the sunlight and convert it into heat. On that part, here at about 10 micrometers, or 10,000 nanometers, this is about the thermal radiation of your solar collector. If you have a solar collector which is 100 degrees Celsius warm, it creates infrared radiation. You can measure that. You can have an infrared thermometer using that. This works in the vicinity of 10 micrometers. So the idea was you want to have high absorption here, but low emission here in that part. So you want to avoid thermal emission here. And this you can do via so-called selective absorber. The property is that it's black in the visible range, or the range of the solar radiance, but in the infrared range it gets white, and also it doesn't absorb, neither emits thermal radiation. And this is called a selective absorber. You cannot see really, if you can see visibly, because our human eye is limited to that, so both appear black to you. But if you measure it at the infrared radiation, you can really see the difference, and you see these huge differences here. Selective and non-selective. So here you can achieve much higher temperatures here, and also at the same temperature you can achieve much higher conversion efficiency. It's not as perfect perhaps here the absorption rate is not so good. You have a bit more reflection because you can get it really a selective absorber as same as good as 100% or a black body absorber. But at the end, if you have here, for example, temperature difference of 75 degrees, here you get only 10% of conversion efficiency, and here you get almost 40% of conversion efficiency, almost four times more. Okay. So come now to the systems. We talked about the collectors now, and now we come to the systems. Very simple system, which is very often used in Brazil, is the so-called thermosiphon principle. So you have here hot water storage with water. There comes cold water in. The cold water goes to the collector. It's getting heated up in the collector, and warm water is lighter than cold water, so it automatically flows up here to a certain rate. So the height difference is quite limited. It's only about half a meter or so. Good for more. And then you store it in a higher position of the storage. So you have some stratification in the water. If you don't mix it up so much, you have here the cold water and the hot water up. And you take away the hot water here. And that's a very common principle. You find it in the Mediterranean, not here Cyprus, or in Israel, or in southern Italy. So this is quite commonly used. Turkey is also quite, so this is a system from Turkey, for example. Here it costs, also Brazil, it costs about 800 euro, something like, depending on the quality and the manufacturer, whether it's stainless steel or whatever. So this is a typical system. They look all pretty much the same. This is in Portugal here. This is even Australia, solar hard. So this is the system. While the buoyancy of the heated water is very low, always the storage has to be very close to the collector. This led to a system in Brazil that's really integrated here. So you integrate the storage almost inside the collector. This is not possible in many countries because it's freezing in winter. And if you want to freezing, you cannot use the water you're using for showering. You can use directly. You have to have different media rather than water. For example, glycol, something like this. If you have glycol, you want to have heat up water, you have to have a heat exchanger. And this heat exchanger needs some pressure, and that's not possible anymore via the buoyancy of the water. So you have to add a pump in order to get it working, to get it running. You have to pump. If you have a pump, you have to have a control also, because in winter, in nighttime, you don't want the system to work. Otherwise, it's more cooling than heating. So you have to. This is system is the control is related to the temperature. So it really detects whether there is some positive temperature gradient between them. So it's only cooling down. You won't let the system work only if the contribution by the collector is positive. The control starts the pump. And then you have here the glycol media here. Then you have a heat exchanger. And then you have, same as in Brazil, the hot water storage. And you take away the hot water here. Sometimes, if you are really winter, you have an additional power supply. Even in Brazil, some people use an electric additional supply to overcome some very bad periods. So there's a software, for example, here the T-Sol. This was my colleague at the Technical University of Berlin. This was his PhD thesis, and he made a lifetime living out of it by making that software. I don't know whether we can start working. There's an explanation of it. I can see the video. No? Is there a way we can switch on the video? No? Oh, no, it's Sophie. Sorry. No, the video doesn't start. Okay, but it's you can also download it here from the manufacturer. It explains the software, but you can find some time to get it started here. Is there someone know over here? Just you have to give some. Just click on the middle of the. Go on the middle, on the middle. Yeah, somewhere, yes, just on the slide, yes. No, it was okay, but it was okay. Just it started. Yeah, just like this. So this is just a. Yeah, it already runs, I think. No.
Está pensando.
The sound is not working. Okay, but we skip that and go continue. We have enough slides for that. Here it shows some the software here. You have pre-configured layouts, and so you can decide whether you have here one storage, two storages, different loads, and so on, and location is determined. So here you have also some buffer systems sometimes, so you have tanks at two different temperatures. You can give in the position here where you are, and then it calculates local irradiance and the output. We have a large data bank of different collector manufacturers, and you can also use it for sizing the area, so you have your requirements, and at the end the program is giving you how many collectors you have to purchase. And this is a fraction. So in Germany, as I told you, winter is very difficult, so you never achieve 100%, or you have a really large storage or large scale power plant. So you only achieve here, for example, 33% of it. There's even a photorealistic option here, so you can with your wife, for example, sometimes they don't like solar collectors and so on, and so you can show how it will look like on your finished house, the collectors, and it gives you an idea of that, how it will look like. Is this finished now, or no? Wait a minute, is this some sound? No, it comes to something. So also yield forecasts, so you have a minute step simulation, operation conditions. So we have here the solar fraction for space heating and domestic hot water supply, tank systems, and so on. This. Here you can have modify that depending on the cost you want related to that, and then the system you have, and then kind of location also plays a role. You also have a profitability calculation, so how much money you invest, what's your interest rate, and how much money you can save or not. Okay, you can also download some trial version. I think it works for, yes?
You can jump this part for solar energy, thermal solar energy, because the Professor Colagino.
Okay.
You cover 90% of my project.
Oh, sorry.
Thank you very much.
Okay.
Better to concentrate in photovoltaic.
Okay, yeah, just because you asked for an historical approach.
I have a question about the less shell length.
Linear lenses?
Yes, another slide that you show.
Yes.
The concentrated lenses. No.
This one. Yes.
Because this type of system increase the temperature, and when you increase the temperature, the efficiency of photovoltaic cells decrease.
Yes. Come to when you talk about photovoltaics. Yes. But this was about concentration of irradiance. This is not yet.
Not for photovoltaics.
Yeah, I think with always concentrator, it just works for direct irradiance. So either Fresnel lenses, or if you have mirror concentrator, it works for concentration only, and therefore you cannot profit from the diffuse irradiance. And also you have to have a tracking system, so it's also costly. So at the moment it's not very much used anymore. You have to do maintenance, you have high investments costs, and you cannot profit from direct diffuse irradiance. So at the moment the profitability of those is a bit questionable. This was about also 20 years ago, so there was a lot of, also because the solar cells have been much more expensive. Nowadays you just buy more solar cells and don't care about efficiency and so on.
We have hybrid systems that
can do both, yes. It was my PhD thesis on 1993, exactly on combination of solar thermal and solar. But I come to this later when I come to photovoltaics. So this was the last slide on solar thermal. So this is software for it, and this just is a working of this. So we hear much more on this tomorrow. So this is also a kind of solar thermal which works with hot air, just to cover area of land, and then the hot air is driving a kind of wind turbine here to create also power. So this is definitely the last slide here of solar thermal. So now we come to the direct conversion of sunlight into electricity. But most of it is used for. This is, you can spend hours talking that and try to do it in 5 seconds, how photovoltaic works. Otherwise, it's turning back. So here you see the working, how does a solar cell work. The most important thing is here you have an electrical field inside a silicon crystal. You can create it by doping here, like an N layer and a P layer. I explained it in 5 minutes. Then you have absorption of sunlight, and during the absorption process you excitate one electron-hole pair. And if the electrical field is strong enough, it can transport away the electron, and it can create an electrical current. Not only through the solar cell, but if you have a closed circuit here, you can supply some load here. And the amount of energy you get there depends on the amount of photons being absorbed and whether the excitation was enough really to be transported. This we'll discuss now in a bit more details. So this is also a video of bricks. I know there's a lot of talk, so I jump over that and explain it manually. Whatever, does it start?
It's a video too.
It's also video.
Okay.
I think there's a lot of talk and I don't know what this guy. Yes, here just on the. I cannot start it from here. Okay, oh, they do this guy talking a lot. No, without better to jump over and I explain it here because this is even quite small. So just explaining the processing of silicon, quartzite into metallurgical silicon. Heating here and tile here put up for takes a while. Perhaps quickly finish the video and I explain the following graphs. So you have the hot silicon melt here, and we take out of the silicon melt here. This is a traditional way, the so-called Tucholsky process. It's not the most energy efficient, but the most traditional process. Historically, most of solar cells have been made like this. So you have a crystal seed, You put it in the silicon melt and you take it out very, very slowly. And then, if you do it slowly enough, then all the other atoms adjust themselves in a crystalline form to the seed crystals. And then you have a monocrystalline ingot, it's called. It's like a very big sausage here, which is up to 1.50 meters or even 2 meters. It has a diameter of 10 to 15 centimeters, and yet you slice that sausage into slices. Usually for electronic industries called wafers. For solar you use it still. Formerly this wafer thickness has been about 0.5 millimeter. Nowadays you have a better source, so-called multi-wire slurry source, which allow sawing losses in the vicinity of only 0.1 millimeters. And also you can make much thinner wafer thicknesses. This avoids a lot of material losses here, and therefore this is also the main reason why solar cells got much cheaper, because you need much less material and also much energy to produce it. This is a Tucholsky process, also more energy efficient, so-called multicrystalline silicon. So you put it into a tile, and then the silicon crystallizes by itself, so you don't have a seed. This is not running perfectly. There are some areas which is a single crystal, but other areas no, it changes direction. So you have, it looks like granite here, so you have here some areas which are a perfect monocrystalline, but then it changes. And the main idea was to insulate these different areas to each other, that there is no current interference between them. And this was achieved in the last years, and therefore these kind of so-called multicrystalline solar cells almost have the same efficiency as the mono or single crystalline solar cells. They are even more cheaper to produce. As a second step, so this is now just silicon, doesn't work yet. We don't have the electrical field inside yet. So what we do, first doping usually takes place already in the silicon. We put, for example, some boron atoms inside the silicon melt. Here, for example, we dope one other side by phosphorus. So there is some phosphorus atoms coming in. And here, for example, here you have a phosphorus atom. So this is the original silicon. And then you have the so-called end-doped silicon, a phosphorus atom. Here, for the silicon, to say that has 4 outer electrons. And these 4 outer electrons combine perfectly in a tetrahedral form with its neighbors. So all outer electrons form a link between the other neighbors here. And here the phosphorus atom, it also starts well here. It has all 4 outer electrons, but there is a 5th electron, which doesn't find a partner here. So this electron is free, it's easily movable. So this is an electron is negative, so this is easily movable, therefore it's called N-silicon. This is done here, in this process here. So we have here some substance containing phosphorus here. Oh, no, okay. On the other side, we have here, as I told you already at the beginning, sometime you pour in some boron. Boron has only 3 outer electrons, and to give a perfect combination with the neighbor, you need theoretically another electron which is not existent. What it's doing, if you miss something, you ask a neighbor. So you take this electron from the neighbor, and this continues like this. So it's like a virtual missing electron, or if you go missing electron or negative electron, it's a positive charge. So this is like a moving positive charge, and therefore it's called p-silicon. If you have 2 of those areas together in one crystal, what happens? There's some diffusion here, for example, because this is easy movable and there's a lack of concentration of electrons here. Some of these electrons move over here. And now the following happens. Before that, there were 5 electrons, but also 5 protons here. So it was electrically neutral. It's called in silicon, but it's electrically neutral. But now these electrons move over here. What happens now? we have more electrons than protons here, and it gets charged negative. So we have negative charge here. This is vice versa, to a bit slower and lesser rate. And then we have negative charge here, positive charge here, and it creates an electrical field. That's what we want. This is essential for the photovoltaic effect. So we create an internal electrical field. It's the same as a diode. If you have some semiconductor glass or something like this, this is just how a diode is created. And now, if here we have the absorption of a photon, then it excitates a silicon atom, so electron is free for a short time. It gets transported along that electrical field which we created there. You have to apply the contacts here. For example, here a front contact. You cannot make it massively because you want to. There's still some irradiance coming in. The back side you can make a massive contacts if you don't have a bifacial module. And yeah, that's a solar cell. This is the characteristics of a solar cell. So you have here first source, a current source, which is triggered by the sun. So the photons. You have a photocurrent, and then you have your diode, which is a parallel to that source. So for each voltage which is above the breakthrough voltage of the diode, it's getting short circuit. Then you have some resistors. This is a series resistor of the grid due to the contacts, and this is a parallel resistor, which is due to impurities in the crystal. And this is our load here. And this is so-called IV curve here of the crystal, so it's negative currents. Should we use it for the diodes here? And so you have here up to a voltage of 0.6 volts. You have a current. If the current is the voltage is getting higher, it's getting short circuit here by the diode here. So this is the area where you can operate in. This is the impact of that parallel resistor here. So if it's infinite, so if it doesn't exist here, so we have a nice line here. So this is if you multiply voltage by current, so you have here significant power output. If this is getting lower here, for example here 100 ohms, then the voltage almost stays the same, but the current is reduced because we have some current losses inside here. And then the power output is also reduced. So this shows how this impacts on the power output. Here we have the same, but for the series resistance, which is related to the contacts. If we have massive contacts, then the series resistance is almost zero, so we would have a curve like this one. If we have high series resistance, we lose some voltage here, because there's a voltage loss over that resistor. And this reduces our power output. Why it's a bit boring just to calculate with negative currents. Here we switch it, we flip it over here, and we take that curve. So here we have the current, and here we have also the voltage here. Here short circuit current, and then we increase the load resistor, and then we come to a point where the product multiplication of voltage times current is maximum. This is the so-called maximum power point. This is where we want to operate the solar cell. You see it here at the red curve, the power curve. So here we have the maximum current, but voltage is zero, so power is zero also. Here we have a voltage of 0.1 volts and a current of about 1 amps. So as you see here, our power output here is about 0.1 watts. So the current stays almost the same, so we increase about 0.4 volts. 1 amp, so we have about 0.4 watts. And that is about the maximum you can get, because now the current stays the same, but the voltage, the current is sinking rapidly, and then the power goes down in a rapid pace. We have one parameter which we will call form factor. This is the multiplication of the voltage, the maximum power point, times the current, the maximum power point, divided by the theoretical maximum, the open circuit voltage, and the short circuit current. So this would form a rectangular form like this one, which is never achievable, but what would be the ideal. And the softer that curve is, the lower is the form factor. The more rectangular it is, the more closer it is to 1. This is the current supply to the load. So this is typically diode formula which we have. So here we have the photocurrent, we have the diode formula here, and the resulting current being supplied to the load. This is open circuit voltage, which is, sorry, I have to ease it a little bit. Sorry. So this is the same for the voltage here. It depends also on the diode identity factor, charge of electrons, reverse rate for terminal voltage here, responsible for the temperature effect. But I wanted to make it more graphically. This you already know here. This is the form factor. This is efficiency here. So you just have the relation of the electrical power output to the incoming power, which is the global irradiance times the area. And this you can substitute by that one. So you have open circuit voltage times short circuit voltage times the form factor. This I mentioned already. These are the standard test conditions in order to compare different technologies and different modules. You have to fix some conditions. Yes? 10 finish. Okay, good. Okay, go quickly. So we have here the temperature, the fixed temperature. That's not the ambient temperature. That's operating temperature. This is rather unrealistic. Usually the temperature, operation temperature, is in the vicinity of 50 or 60 degrees. But it was once agreed to that, and so all laboratories, they just have to use that temperatures. But it's not really realistic. And you have the irradiance here, 1,000 watt per square meter. This is bright sunshine. So in Germany, it almost never occurs, here more often. And I talked already about the spectrum according to air mass 1.5 and perpendicular irradiance. So this is should you keep in mind if you just get the solar modules here. This is already mentioned here. So this is air mass again. So this was just a repetition here of the irradiance part. But now we add our sensitivity of our solar cell here. So this is what a solar cell can convert. Here there's some limit for longer wavelengths, because then the energy would not be enough to liberate an electron and then create a flow and power production. On the lower side, it's the opposite, that the photon delivers more power than needed because you only create one electron at a given voltage. That means the power output is constant, but the input power is increasing. That means your efficiency is going down. So therefore you have this typical form of two limits, upper and a lower limit, or lower and lower efficiency at the lower reduced wavelengths. This, for example, this was for crystalline silicon. This is now for amorphous silicon. This is more sensible, for example, in the blue part of the spectrum. This, for example, for carbon telluride, which is a little sensitive. Therefore, it's important always to think about the spectrum, because it has an impact on the efficiency. This is also one of the most important curves of ID characteristics. So you have here the cell, the solar voltage of the solar cell, and the current here again. This is under standard test conditions, 1,000 watt per square meter. You have the maximum power point. And if you reduce the radiance, what will happen? You create less, you get less photons. That means less electrons. And so the current is directly proportional to the irradiance. So 10% of the irradiance means you have 10% of the short circuit current. Here we have something special. Usually we should expect the voltage stays the same, but actually that's not the case. Why? This is due to we have the equivalent circuit here. Go back to the equivalent circuit. While we at low irradiance level, what we have to do to keep the module working in the maximum power point if we have low irradiance level? Do we have to increase or decrease that load resistance?
Increase your resistance value?
Increasing?
Your resistance value?
Yes, this is the load resistance. And now we go from high irradiance levels to low irradiance levels. What happens?
The load reduced, the current?
Yeah, the current is reduced. Voltage stays about the same. That means low current, high voltage is increasing the load. Exactly, we have to increase the load resistor in order to keep it working in the maximum power point. This is a following impact. This is all inside the solar cell. We cannot change it. So this also stays the same. And then the distribution is a bit different because now is high resistance here. This resistance stays the same. So there's a higher share being lost inside the solar cells due to this parasitic parallel resistor, which is due to the impurities in the solar cell. So we lose more here relatively. And this you can see here on this curve. Here, on that curve that you see here, for low irradiance levels here, we have some losses here, and the maximum power point is also a bit shifted. So besides having low power output due to the irradiance level, we also have a reduction in efficiency, unfortunately. So this is provides a lower efficiency than than originally given. This is called the weak light effect. I discuss and show it afterwards, what's the effect of it. Another effect is temperature. Temperature, as you saw before, is temperature dependent. And here you see if we increase the temperature, here the dashed line is the standard test conditions here, 25 degrees. If we increase temperature, voltage is going down. The current is a little bit increased because the solar cell gets more sensible in the infrared region. So we increase current a little bit, but in general we reduce voltage and also power output. So this depends on the solar cell technologies, so in the vicinity of 0.5% per Kelvin of increase. Here we have a table here which shows the different technology and the reduction of power output, for example, for multicrystalline silicon, which is the most often used nowadays. You have a reduction of minus 0.44% per Kelvin. For current, it's even a bit decreasing. And here the coefficient is also temperature dependent, so the form factor is also temperature dependent, and also the decreases a little bit with temperature. There was one table I just want to mention here, as NOCT. It's called nominal operating standard test conditions, which is not equivalent to the standard test conditions, but it would be more appropriate to that because it would not consider only cell temperature, it would consider the actual ambient temperature and then the actual operating temperature, which develops depending on the cell technology and so on. And also consider the wind speed and global irradiance level, which is not that bright sunshine, a bit reduced, 800 watt per square meter, and also elevation of the module. The output, according to the NO's nominal operating conditions or the nominal operating temperature, is here you see the temperature much elevated than 25 degrees we have at standard test conditions. This is much higher, and therefore power output is lower, also due to the lower irradiance level. And while it's lower, the industry didn't accept it because they want to have high numbers and show off a lot. But this would be more realistic for the science community. This would be more relevant. But unfortunately, the standard test conditions are now the most dominant you use for that. But this is more realistic. So from this NOCT, just keep in mind that some of the time you find those conditions. Here for NOCT, there's a norm for that, how to measure it. If you can't achieve the ambient temperature, there's a compensation chart for it. Also, you can have the quick overview about the temperature you can achieve. So you saw this 45 degrees for many models, but if you, for example, have a rack mount, for example, for free mount installation, you get even a lower temperature by 3 degrees. If you directly mount on the surface of a roof without any ventilation, you have an increased temperature by 18 degrees. If you have some air gap in between, then the air can fluctuate, and here you see as bigger the air gap is, the lower is the operation temperature. So we are almost at the end, or shall I?
Hours.
Huh?
You need to finish.
Okay, yeah, so we go to the next chapter. Yeah, we have
After lunch.
Yeah, so we have more actually capital.
You need to return some minutes after 12.
So we return what is the schedule? 2 p.m. 2 p.m. we will be back, and you can